back to...
Time's limited, so you must listen carefully.
Hello, and welcome back to... a Student Course Survival Guide. Today we're going to talk about... petroleum. Mina Donishvar.
I don't think I understand. I don't think I ever could.
Petroleum. And we're here to make learning petroleum just a little bit easier.
You know what we've done, gang? We've defied all the laws of nature. That's what we've done. We've created a living, breathing, bending man out of sheets of paper and little plastic cards.
Today, we'll look at gases and the equations of state. Understanding compressible fluid behavior is important not just as a petroleum engineer, but throughout the world. Compressible flow analysis is used in understanding the speed of sound, how to determine a blast radius, and of course in producing my favorite sparkling wines. The periodic table of elements. Gas elements are denoted by the red color. In my experience, I've only really used the table for the molecular weight of elements, but if you specialize in drilling fluids or such, you might use it a little more. It's probably safe to assume that at this part of your academic career, you've been exposed to the ideal gas law, first stated by Emile Clapeyron. An ideal gas assumes 3 points. First, that the volume occupied by the molecules is insignificant with respect to the volume occupied by the gas. Second, there is no attractive or repulsive force between the molecules or between the molecules and the wall of the container. And lastly, all collisions of molecules are perfectly elastic. That is, there is no loss of internal energy upon collision. In the equation PV equals nRT, P stands for pressure, V for volume, T for temperature, N the number of moles, and R the ideal gas constant, which I learned to remember as pervnert. I want to talk about the kinetic theory of gas real quick, just as a conceptual base, since gas theory will haunt you to the end of days. Anyway, according to gas theory, the molecules of any substance are in a constant state of motion at all temperatures above absolute zero, which is why we have temperature units of Rankine and Kelvin. The molecules of a solid are restricted in their movement by the attractive forces which hold them near a fixed position, so that the motion corresponds to the molecular vibration rather than to actual movement of the molecules. This is true to a lesser extent in liquids, in which all the molecules both vibrate and move around. Molecules of an ideal gas are completely separated from each other and move with an average velocity. Molecular velocity increases as the temperature of the gas increases. Temperature, therefore, is simply a measure of velocity, or the kinetic energy of molecules. Gas molecules undergo a tremendous number of collisions with other molecules and with the wall of the container, so the directions and velocities are constantly changing. Pressure is simply the combined effect of all of the collisions of the molecules with one another and with the wall of the containing vessel. The number of moles or amount of substance denoted by the letter N is defined as the total mass of a substance divided by its molar mass. So, the ideal gas law can be rewritten in terms of density by replacing N with its definition. then written to display density's definition, mass divided by volume, and finally, you have the ideal gas law in terms of density. Likewise, it can be rewritten in terms of specific volume. Combined Boyle's, Charles, and Avogadro's equations show that PV over T is a constant between states and leads to the ideal gas constant R. For a specific gas, the universal gas constant R bar is divided by its molar mass, leading to these further definitions. Next, we'll discuss mixtures of ideal gases. First, it's worth noting how molecular composition is written, Y sub J, referring to the fraction of gas occupied by the component. Dalton's laws of partial pressure, written by John Dalton in 1802, states that the total pressure exerted by a mixture of gas is equal to the sum of pressures exerted by its components. The pressure exerted by each component gas is the partial pressure. Basically, the pressure a single component gas would exert is its contribution to the total pressure. This law is sometimes called law of additive pressures. We can prove this using the ideal gas equation for a multi-component system, with component A having Na moles, B, Nb, C, Nb, etc. So partial pressure of each is defined as Pa equals Na RT over V. Sum of the partial pressures is the total pressure. P equals the sum of Pa, Pb, Pc, etc. Ratio of the partial pressure of component J to the total pressure of mixture P. Partial pressure of a component is then as follows. Similar to Mr. Dalton, in 1880, Émile Amagat postulated that the total volume occupied by a gas mixture is equal to the sum of the volumes that the pure components would occupy at the same pressure and temperature, also known as the law of additive volumes. The volume occupied by the individual components are known as the partial volumes. Again, consider a gas mixture of components A, B, C, etc., each with a number of moles. The math is the same. Hit pause if you need. Since a gas mixture is composed of molecules of various sizes, saying a gas mixture has a molecular weight is not exactly correct. However, a gas mixture behaves as if it has a definite molecular weight, which we can define as thus: the sum of component molar vapor fraction times the component weight. While there are hundreds of equations of state for real gases, we'll focus on the one used most commonly in the oil and gas industry. What's new from the ideal gas equation is a correction factor on the right side denoted by Z, or Z. The Z factor is the compressibility/gas deviation factor and is the ratio of volume actually occupied by the gas at a given pressure and temperature to what the gas would occupy at the same pressure and temperature if it behaves like an ideal gas. Z factor is not constant and must be determined experimentally, but there's charts for our uses. This figure shows the typical shape of the Z factor as a function of pressure at a constant temperature. We can see from this figure that this checkmark curve shows that at a low pressure range, when Z is less than 1, that the actual gas volume is less than that of the ideal gas volume. At moderate pressures, the molecules are close enough to exert some attraction between molecules, causing the actual volume to be somewhat less than the volume predicted by the ideal gas equation. At higher pressures, the actual volume is larger than that of the ideal. Here, the molecules are forced close together. Repulsive forces come into play, and Z is greater than 1. At Z equals 0 and pressure equals 0, the gas acts ideally. This is because the molecules are relatively far apart with low pressures. It is also evident from this plot that the Z factor will vary with gas composition, temperature, and pressure. I'm including the plots for methane, ethane, propane. This is more so you can see and understand the general shapes rather than trying to read the fine print. But hit pause and squint if you so desire. The law of corresponding states say that all pure gases have the same Z factor at the same values of reduced pressure and reduced temperature. Further, for gas mixtures, the physical properties of gas mixtures are correlated with pseudo-reduced temperature and pseudo-reduced pressure in the same manner that the properties of pure gases are correlated with reduced temperature and reduced pressure. Here is a plot of Z factors at reduced pressure and reduced temperature for ethane, propane, N-pentane, and N-hexane. Recall our gas formation volume factor, a similar ratio of gas volumes. Ideal gas volume at a given pressure and temperature is divided by the volume at the constant standard conditions. In terms of real gas law, we define Bg as V divided by SC volume. At SC pressure, P equals 14.7 psia, T 520 Rankine, and Z1, leaving us with a Bg of 0.0283 ZTP. Next, we'll introduce the compressibility term you're most likely to encounter and work with, coefficient of isothermal compressibility. It can be derived and denotes the change in volume per unit volume per pressure change at a constant temperature. If you're familiar with other applications, this might look like the specific heat value. While understanding enthalpy is important to success in engineering, it's not important in this particular application, but it is assumed that this process is isentropic and isenthalpic, meaning that enthalpy and entropy are constant. Compressibility and formation volume factor both help us understand our fluid and down the line our reservoir and other production systems. That does it for our equations of state and compressibilities topic. Don't forget to like and subscribe. I'm also available to answer questions about this or other petroleum engineering topics at petroleum.studentsurvival@gmail.com and support us at patreon.com/petrole_. Thanks.